Welcome to Learning Podcasts. Protobuf, Chapter 5. Maps are just repeated messages.
By the end of this chapter, one of the 4 features we cover is going to look strangely familiar.
You are modeling a user account. The status field can be active, suspended, or deleted. So you reach for a string. One service writes lowercase active. Another writes capital A active. A third gets enthusiastic and ships active in all caps. All 3 are valid Python. All 3 pass code review. All 3 deploy. And somewhere downstream, a switch statement only matches one of them.
3 valid spellings, 3 potential bugs, 0 compile time protection.
Protobuf gives you the enum. You declare it with the keyword enum. You give it a camel case type name like account status. And inside curly braces, you list each value with a name in upper snake case and an integer assignment. So account status contains account status unspecified equals 0, account status active equals 1, account status suspended equals 2, account status deleted equals 3, a named set of integer constants. The string is gone. Typos become compiler errors.
1 source of truth, 1 valid set of values.
Now look at the value names. Every one of them starts with the type name. Why all that ceremony when the values already live inside an enum block? The answer is a quirk inherited from C++. Protobuf uses C++ scoping rules for enums, which means enum values are not scoped to their containing type. They live at the same level as the enum itself. So if you defined 2 enums in one file, and each one had a bare value called active, the compiler would refuse the file. 2 definitions of active at the same scope. Prefixing every value with the type name in upper snake case sidesteps the collision entirely.
Strict-looking convention. Real-world reason.
The first value in a Proto3 enum has to be 0. That is a hard rule, and it is not arbitrary. In Proto3, when a field is not explicitly set, it deserializes to the 0 value. For an enum, that is whichever name you put at 0. So picture the alternative for a second. You make active the 0. A sender that explicitly sets the status to active looks identical on the wire to a sender that never set the field at all. You have erased the difference between known and unknown. The convention, baked into Protobuf style guides, is to make the 0 value an unspecified entry. A meaningful business value never sits at 0.
Otherwise, unset and active mean the same thing.
On the wire, an enum is encoded exactly like an int32 using the var-int encoding from Chapter 4. Same bytes, same wire type. No overhead compared to a plain integer, but with compile time safety you do not get from a raw number.
Cheap on bytes, expensive on bugs avoided.
Beyond scalars and enums, real messages contain other messages. A user has an address. An order contains line items. Protobuf lets any message reference any other message as a field type, and it lets you define a message inside another message, which is called a nested message. Picture a user message that needs a home address. You could define address at the top level of your proto file. That works if address is shared across many messages. But if address only ever appears inside user, defining it at the top level just clutters the namespace. So you define address inside the user block and reference it directly.
1 organizational choice, no wire format consequence. What does that nested type look like in generated code? In Java, the nested address class is exposed as user.address. From outside user, you reference it with the qualified name. From inside, the short name is sufficient. In Python, it appears as a nested class, accessible through the outer class. Same idea. And on the wire, there is no difference between a top-level message used as a field type and a nested one. Both are encoded as length-delimited values, wire type 2. 1 variant byte count followed by the serialized inner message.
A user might have 1 email address or 5. An order might contain a single line item or dozens. To model collections, you put the keyword repeated before the field type. So repeated string emails equals 5 means field number 5 holds 0 or more strings. The generated code exposes this as a list in Python and a repeated field accessor in Java. The sequence is ordered, and elements come back in the order they were added.
Same field number, many values.
On the wire, the encoding depends on what the elements are. For messages and for strings, each element gets its own tag length value entry, and they all share the same field number. The decoder collects every entry it sees with that number and assembles a list, preserving the order they appeared in. There has to be a length prefix on each one, because a string or a message has no fixed size. Without the per element length, the decoder would not know where one element ends and the next one begins.
One tag per element, lengths everywhere.
Repeated numeric scalars get a smarter treatment. By default in Proto 3, they use packed encoding. Instead of a separate tag per element, the encoder writes one tag with wire type 2, one varant byte count, and then all the values concatenated back to back. So a repeated int32 holding 10, 20, 30 becomes one tag, one length, 3 varants. Each value is still a varant from Chapter 4, just stored back to back without per element tags. That is a real saving when a list contains hundreds of small integers. The reason strings and messages cannot be packed is the one we just covered. Each one needs its own length prefix.
Tags on the outside, varants on the inside.
The fourth feature is the map. You declare it as map, angle bracket, key type, comma, value type, angle bracket, then the field name and number. So map, angle bracket, string, comma, int32, angle bracket, word underscore counts equals 1 defines a mapping from strings to 32-bit integers. The generated code exposes it as a dict in Python and a map accessor in Java. Key plus value plus field name plus field number.
Familiar shape, new keyword.
There are constraints. The key type has to be an integral or string scalar. So int32, int64, uint32, uint64, synt32, synt64, fix32, fix64, sfix32, sfix64, bool, or string. Floating point types, bytes, enums, and messages cannot be keys. The value type can be anything except another map. No nesting maps inside maps. And there is one more thing the docs are explicit about. Maps are unordered. Serializing and deserializing a map may reorder the entries. If insertion order matters, you do not want a map.
If order matters, reach for repeated, not map.
And here is the title of this chapter. A map field is syntactic sugar. The compiler does not generate a special wire format for it. Under the hood, it treats map, angle bracket, key, comma, value, angle bracket as a repeated nested message with 2 fields, a key field at number 1 and a value field at number 2. So a map with 3 entries on the wire looks identical to 3 instances of that little nested message. Same length delimited entries, same field numbers, same bytes. The fourth feature in this chapter is the first 3 composed.
So old code that predates map syntax can still decode it as a repeated field. That is how the format stays backward compatible.
Each feature fills a distinct role. Enums for a closed set of states known at schema time, nested messages for substructure that belongs to one specific parent, repeated fields for ordered collections of any size, maps for unordered key value lookups, even though under the hood the wire format is reusing repeated nested messages.
4 tools, 1 wire format underneath all of them.
You now have the Protobuf vocabulary for modeling real data, closed sets, substructures, ordered lists, key value lookups, all with compile time safety and predictable wire encoding.
Next chapter, we look at one of and optional fields, 2 features that let you express mutually exclusive choices and explicit presence inside a single message.
Thanks for listening to Learning Podcasts.